Then the continuation of manufacturing process of ceramics. Then the chemical reaction of clay. Here you can see this. The clear flow chart will be given. Okay. When heat to 1100 degrees Celsius air Kelvinite decomposes by the first order kinetics. After that, what will happen? According to this, the following sequences will be taken. The step one is very important step. The temperature must be carefully controlled as the clay decomposes. The water given out by this reaction is not water remaining between the particle but what bound onto the mineral lattice. The loss of this water causes the lattice and ends the clay particles and therefore the clay body to shrink. If this state is not carefully controlled, the body can be destroyed by thermal stresses and by the rapidly escaping steam. The weight loss during the step 1 is about 14%, which means that the volume of steam evolved at 550 degrees Celsius from a 3 kg lump of clay would be 2 meter cube at a standard temperature STP. A large masses of clay were being fired in a kiln must be well ventilized. Next, step 3 and 2 is explained in the 2 and 3 is explained in the flowchart. Here you can see the mineral undergoes further solid state reactions where the parent crystal is rearranged and the silica is rejected in the form of glass. Finally, at 1250 degrees Celsius, the mullite and silica glass remains the same. Then the chemical reaction of silica. Silica will not decompose at the temperature encountered in the firing kilns and melts at 1725 degrees Celsius. Chemical reactions of feldspar. Pure feldspar grains begin to melt at about 1140 degrees Celsius to form a solid and viscous liquid. As the temperature is raised, the solid decomposes to form more liquid. Combined chemical reactions. The clay body consisting of the above compounds is heated sufficiently. All the above reactions occur as well as the several others. The other reactions are between the compounds themselves. In the step 1, the decomposition of Calton reaction. This is then followed by the step 2, the decomposition of metacalotin kelonite to form a silicon spiral, and then between 1000 degree to 1100 degrees Celsius mullite crystal form and silicon dioxide glass to begin to form in this step 3. Mullite crystals remains in the vicinity of the clay particle. At 1140 degrees Celsius, 140 degrees Celsius, feldspar grains are smaller than about 10 meter have completely dispersed. It's not 10 meter, maybe it is 10 mm that have completely disappeared by reaction with the surrounding clay. The alkali metals ion diffuse out of the feldspar and the remaining solid decomposes to form mullite and silica rich liquid. If the body is fired to about 1250 degrees Celsius, the alkaline metal ions, potassium plus sodium dissolves on the outer layers of the quartz particle in a silica glass containing alkali metal ions. This glass cements the whole structure together and makes it non-porous and water-light. Then in step 4, glazing. Glazing is a thin layer of a glass or glass and crystal that adhere to the surface of the clay body. It provides a smooth and non-absorbent surface that can be colored and textured in a manner not possible on the clay body itself. Glazes are composed of various oxides combined in a proportion that will yield the desired properties. Silica dioxide and boric oxide, B2O3, they are the glass formers, but oxides such as the sodium oxide, get to potassium oxide, calcium oxide, then PbO and aluminum trioxide must be present in the stoichiometric sense to give the desired properties. These include, for example, lowering the viscosity of the molten glasses so that a glass will flow smoothly over the surface of the clay body at the temperature at which the clay, glaze is fired. The glaze is either applied before firing or between a first and second firing. Glazes are glazy substance used to provide a smooth surface on the item and to color the ceramic surface. Glaze application. If a plain colored article is being produced, the glaze is either applied by dipping or spraying. For pattern, the pattern is printed on a special machine, one color at a time, with a maximum of 3 colors. Some patterns are hand printed. When glaze is applied, the article go through the second glazing film, taking up to 12 hours cold to cold go go through and reaching a maximum temperature of 1050 degrees Celsius. Some patterns are put on after glazing by transfer process, and these articles then go through another oven at a temperature of 720 degrees Celsius. So these are things that are glaze applications. Next, colors of glazes. Here you can see this, we are using the various colors: blue, green, red, black, and yellow. So with the help of the following chemicals, we can form the commonly used in the forming of glazes. Okay. Then the figure shows the different techniques for processing a advanced ceramic. Here you can see the first ceramic powder. We are taking the ceramic powder. After the ball milling, blending, and spray drying operation, binder substance, we are giving this a degassing. After that, it will be applied to the hot pressing process or hot isostatic pressing process. Then in this process, after this process, we are given to the secondary machining operation or final finishing operation. Then the final product we are getting. In case after this process, it will be given to the slip casting. The slip casting process we are applying to the drying. Then the drying, after drying process, the green raw material will be taken to the binder burnout process or centering process or compact process. After the compact process, given to the secondary machining operation or final machining operation. Then it will be given to the final sintered ceramic product. Then application of ceramics are. Then text application of ceramics are glazes, glass and ceramics. Clay products are structural clay, product, whiteware. Then refractives are fire clay, silica, base and special. Then abrasives are sandpapers, cutting and polishing. Okay. Then cement and advanced ceramics. So these are the applications of ceramics. Then application and processing of ceramics are glasses, clay products, refractive. Then in the clay products, structural clay product, white pass or we already said. Then refractive, fire clay, silica, basic refractive, special refractive. Then abrasive, cement and advanced ceramics. So these things and these things and Then in the clay product, structural clay products, ceramic products are intended for use in the building construction. Typical structural clay products are building bricks, paving brick, terracotta facing tile, then roofing tile, and drainage pipes. These objects are made from commonly occurring natural material which are mixed with water, formed into the desired shape, and fired in a kiln in order to give a clay mixture of common form. So next, whiteware. Here you can see the whiteware, the application of whiteware. You can see this. Any board of clay, a class of ceramic products that are white to off-white in appearance and frequently contain a significant vitreous or glass. Here you can see the included products as a diverse, fine china and other porphyry, then floor and wall tiles, then dental implants, electrical procline, then decorative implants. These are the simple examples. Then refractives. Here you can see the bricks, refractory bricks, fire brick for furnace and ovens have high silicon and aluminum oxide content. Brick products are used in manufacturing the plant for iron and steel. Non-ferrous materials, glass, cement, ceramic, energy conversion, and petroleum. These things are all example. Then refractors. Here you can see this refractors are given. A group of ceramic material capable of withstanding high temperature for prolonged period of time. That is a very important part. Then acid refractors. Common acid refractors include silica, aluminum, and basic refractors are number of refractors are magnesium oxide. That is magnesia or perclase. Then neutral refractors are these refractors are which include chromite or and chromite magnesite might be used to separate acid and basic refractors, preventing them from attacking another. So here they are given figures show the manganese Mg2 SiO4, then Fe2 SiO4 phase diagram showing completely solid. This is a simple refractors, composition of typical refractors. Here you can see this the fire clay. Okay, fire clay then will be made about. It is the type of clay which is used to production of the heat resistant clay items such the crucible used in metal manufacturing. This type of clay is commonly mined from the areas around the coal mines, although other natural deposits and also available as a potential source, with many nations having deposits of clay suitable for use in the high temperature applications. Silica, yeah, they are made from the quartz and silica gravel deposits with a low aluminum and alkaline contents. Here you can see the chemically bonded with 3 to 3.5%. Okay, then the silica refractors have the good load resistance at high temperature, are abrasive resistant, and are particularly suited to containing acidic slags. Okay, here you can see the special refractors, and this is the basic refractors. Okay, then advanced ceramic materials have been developed over the past half century. Include the industrial inorganic ceramic chemicals. We already saw that one of the inorganic that exhibits specialized properties require more sophisticated processing. Engine applications are very common for this class of material, which includes silicon nitride, silicon carbide, zirconia, and alumina. Okay, and heat resistant and other desirable properties have led to development of methods to toughen the material by reinforcement with fibers and viscous, opening up the more application on ceramics. Structural application, electrical application, and coating, chemical. Here, structural applications are applied for as a thermal barrier coatings to protect metal structures, wearing surface, wear parts, or integral components by themselves. Bioceramic, engine components, armor. In the electrical, capacitors, insulators, integrated circuit packages, piezoelectrics, then magnets and superconductor. N is specially coating, engine components, cutting tools, and industrial wear parts. Then the chemical and environmental filters, membranes, crystal catalysts, and catalyst supports are used. So here you can see this application of advanced here. Presuming S3, Si3, N4, gas turbine rotor, then alumina rotor, then boride. Okay, it's a nozzle made up of board income WC, then gears made up of alumina, then structural. Okay, parts that is also made up of alumina, then pendant magnetofrefractive bricks. Okay. Then some of the applications are electronic applications and the engine applications are given. Possible parts, engine valve, pistons, jet engines. Okay. Then the disadvantages are this is the brittle one, too easy to have voids weaken the engine, difficult to machine. There is a very important disadvantage. It is a difficult to machine. Advantages run at a high temperature, excellent wear and corrosion resistance, low frictional losses, ability to operate without a cooling system, low density.